Imagine you're the pilot of this massive commercial jet, right? You're cruising at 30,000 feet, hundreds of lives on board, and everything seems totally fine. But the catch is that every single instrument you need to fly this plane, like the altimeter, the fuel gauge, the navigation system, they all operate on completely different control panels.
Oh, wow.
Yeah, and those panels are located in entirely different rooms of the aircraft.
Right, so to check your altitude, you have to literally leave the cockpit, walk down to row 12, and interpret this proprietary screen that, I don't know, only outputs data in French.
Exactly. And then to check the engine temperature, you're climbing down into the cargo hold to read some dial manufactured in the 1990s.
Which is terrifying. I mean, you technically have all the data you need somewhere on the plane, but the operational telemetry is so heavily siloed that by the time you've actually aggregated it, the plane might already be in a nosedive.
And we are looking at that exact scenario today. Just, not in the sky. We're looking at it on the ground.
Welcome to another deep dive. Our mission today is to decode the immense complexities of modern data center management, specifically bridging that massive gap between software-defined architecture and the raw physical heat-generating hardware underneath it all.
Yeah, because the digital infrastructure that's powering everything from your daily cloud syncing to, advanced distributed AI training workloads, it is facing a massive crisis of fragmentation right now.
It really is. And for our sources today, we are relying on some foundational groundwork laid by an internal 2024 presentation deck from the Supermicro SuperCloud Composer, or SEC, Taiwan team.
Right, getting insights directly from product managers and engineers over there, guys like James Shai, Eric Chang, Danny Peng, and Jinhao Chang from the SEC, PM, and support teams. It gives us a direct look into the actual trenches of this infrastructure crisis. Definitely. So we are going to figure out exactly what SuperCloud Composer is, why modern data centers are basically hitting a brick wall without unified management, and how this platform tackles everything from network orchestration to physical liquid cooling leaks. Okay, let's unpack this.
Well, we really have to start with the specific friction points that IT administrators are hitting today. Because when you walk into a modern data center, the physical layout looks highly organized, right?
Yeah, endless rows of racks, perfectly aligned, blinking lights.
Exactly. But digitally, underneath all that, it is deeply fragmented. Data centers are what we call brownfield environments, meaning you are almost never just running brand new hardware across the board.
Right, you've got architectures from multiple different vendors spanning several generations.
Yeah, you could have an air-cooled server blade from 2018 sitting right next to a liquid-cooled GPU cluster from 2024. And their baseboard management controllers, they do not naturally speak to one another at all.
Because they rely on entirely proprietary management software, right?
Exactly. So IT administrators are constantly context switching. They're jumping between different isolated tool sets just to monitor base-level hardware health. And the industry has been chasing this concept of ODM-like infrastructure management for a while.
ODM being Open Distributed Infrastructure Management.
Right. The goal is a centralized vendor-agnostic control plane, because without it, trying to scale lifecycle management across these distributed environments, it just introduces massive inefficiencies.
I can imagine.
I mean, if you try to deploy a rolling firmware update across a fragmented architecture using 5 different tools, human error inevitably creeps in, and that leads to inconsistent performance and really costly downtime.
And that fragmentation, it also creates a severe vulnerability in your security posture, particularly around role-based access control, or RBAC.
Oh, absolutely.
Because if your centralized security system doesn't have a unified real-time view of what a specific server is doing, because that telemetry is trapped in some proprietary vendor silo, you lose granular metadata context.
And metadata context is literally everything in modern zero-trust architecture.
Right.
If the central system cannot verify the exact state, the network location, or the current workload of a piece of hardware, it just cannot enforce least privilege access accurately.
So what happens? Administrators just end up over-provisioning permissions.
That's exactly what happens. They grant these broad, sweeping administrative rights to a user just so that user can execute one localized maintenance task, and then you end up with standing privileges that widen your attack surface exponentially.
Okay, I want to push back on the viability of solving this, though. Because building a unified control plane for a greenfield environment where you just buy all brand new hardware from one vendor, that's one thing.
Sure.
But with the brownfield reality we just discussed, how do you actually force a 2018 proprietary system and a 2024 AI cluster talk the same language, like without building thousands of custom integrations that are just going to break during the next software update?
That is the million-dollar question. And the mechanism that makes this possible without those brittle custom integrations is the implementation of a standardized Redfish northbound API message bus.
Okay, Redfish API.
Yeah, rather than trying to force the hardware to learn new protocols, SCC uses this message bus as an abstraction layer.
I like to think of it like a universal UN translator for your hardware. You have all these different components speaking their native proprietary dialects on the southbound side, right?
Right, down at the metal.
But instead of talking directly to each other, they publish their telemetry to the message bus. And then the bus translates and normalizes all of those hardware calls into the standardized Redfish RESTful API format on the northbound side.
Exactly. So any third-party software, monitoring tool, or automated deployment script, it only needs to know how to speak Redfish.
Which makes it so much simpler.
Totally. They just query the central message bus, and SEC handles all the complex routing and translation down to the physical metal. It completely decouples the management software from all those underlying hardware quirks.
That makes sense. And that brings us to how the operators actually interface with this abstraction layer. The solution built on top of this architecture is SuperCloud Composer.
Yeah, SCC.
It's positioned as a rack-level management platform for software-defined data centers, and it integrates compute, storage, networking, and physical rack management all into a single cohesive UI.
And the human factors engineering on that dashboard is incredibly deliberate.
How so?
Well, SCC utilizes standardized icon footprints for event tracking across the entire hybrid environment. Think about it. When an infrastructure engineer is staring at a monitor at 3:00 a.m., responding to a cascading failure, they do not have the cognitive bandwidth to decipher 20 different vendor-specific warning symbols.
Oh, for sure. A blinking red light on a Dell shouldn't mean something totally different than a blinking red light on a Supermicro.
Exactly. So normalizing the visual feedback across multi-generation Supermicro servers, whether it's GPU, Twin, Blade, or storage and third-party systems, it massively reduces the cognitive load. It really accelerates incident response times.
Now, obviously, getting access to this level of orchestration depends heavily on your deployment scale. There are specific licensing realities here that we should touch on.
Right. It's not a one-size-fits-all.
Yeah, for full enterprise-grade orchestration, you are looking at a combination of licenses. It's the SFT SDDC single and the SFTDC MS single licenses.
Yeah, that gives you the whole software-defined data center suite.
But if your footprint is smaller, maybe you strictly need fundamental server management without the broader SDDC capabilities, then just the DCMS license handles that baseline.
And Supermicro scaling the software access based on deployment complexity, it just makes sense. I mean, not every localized edge deployment requires the massive orchestration overhead of a hyperscale facility.
True. But let's look at that active orchestration for a second, because a dashboard that merely visualizes a Redfish message bus is ultimately just a reporting tool. A pretty pane of glass doesn't help me if I still have to manually SSH into 100 different machines to actually fix the problems it's showing me. So how far down the stack can SEC actually reach to manipulate the hardware?
Oh, it reaches all the way down to the bare metal. SCC isn't just a passive monitor, it executes active lifecycle management.
Like what kind of tasks?
We're talking about orchestrating complex OS provisioning at scale with minimal downtime, pushing out baseline configurations, and executing mass firmware updates across those heterogeneous clusters, all through the Redfish API.
Wow.
But if we connect this to the bigger picture, the most aggressive active management capability is how it handles storage. Specifically, its support for pooled NVMe over Fabric.
Oh yes, pooled NVMe over Fabric.
Yeah.
That fundamentally breaks the traditional limitations of server architecture.
It really does.
Because historically, your high-speed storage was physically trapped on the local PCI lanes of a specific motherboard, right?
Yep, completely locked in.
So if server A is totally bottlenecked on compute but has like terabytes of idle flash storage sitting there, and server B is starving for storage but has plenty of compute power, server B couldn't touch server A's drives.
Exactly. But NVMe over Fabric detaches that storage logically. It pools those high-performance drives together and then serves them across the high-speed network fabric, and it utilizes remote direct memory access protocols to maintain microsecond latency.
So it's basically as fast as if it were plugged right into the board.
Pretty much. And SCC is the orchestration layer that actively manages this dynamic allocation. It slices and assigns those pooled storage resources to specific workloads on the fly, depending on real-time demand.
So you are completely decoupling the logical resources from the physical chassis.
Yes.
But, and this is a big but, that dynamic allocation introduces a massive physical problem. When you are shifting heavy compute and storage workloads dynamically across the fabric, you are creating unpredictable localized heat spikes in the physical data center.
Oh, 100%.
Software-defined flexibility creates physical chaos that traditional HVAC cooling systems simply cannot respond to fast enough.
The physical environment is always the ultimate bottleneck, and that is exactly why SCC integrates the Power Distribution Unit console module directly into the same software-defined dashboard.
So bridging the gap again.
Right. You cannot manage dynamic workloads without managing the power draw. The platform utilizes a hierarchical tree view to present asset information and sensor data.
And that spatial mapping is critical, because if your telemetry indicates that a specific node in a pool is drawing way too much power and overheating, knowing its IP address isn't enough.
It doesn't help you physically find it.
No. The hierarchical tree maps the logical telemetry back to the physical rack layout, so a facilities engineer knows exactly which server in a room of 10,000 machines needs physical intervention.
And here's where it gets really interesting.
Yes, here's where it gets really interesting.
We have to talk about how it handles the thermal density of modern workloads. Air cooling is rapidly hitting a physics limitation, especially with these high-density GPU clusters.
They just run way too hot.
Exactly. The thermal design power of these chips requires liquid cooling, which suddenly forces IT administrators to manage basically fluid dynamics. And SCC tackles this with the Liquid Cooling Console Module, or LCCM.
It's pulling telemetry directly from the physical plumbing.
Literally.
It connects to the cooling distribution unit, the CDU, and the external cooling towers.
Yeah.
So we are looking at data points like the IP addresses of the pumps, the exact actuation status of individual valves, localized pressure levels, ambient humidity, and real-time coolant temperatures and flow rates.
And the platform ingests that industrial telemetry to close the feedback loop on cooling cost-effectiveness.
Oh.
Because in a legacy setup, pumps just run at a static pressure, which wastes massive amounts of energy when the cluster is idling.
Right, they're just pushing water at max speed for no reason.
Yeah. But by tracking the exact thermal output of the servers against the flow rates and return temperatures, SCC can dynamically throttle the liquid cooling pumps. It matches the cooling expenditure perfectly to the real-time compute load, which drastically optimizes the overall power usage effectiveness of the facility.
It's like a highly advanced smart home system. It doesn't just tell you the house is hot, it actively intervenes. But the stakes with liquid cooling are incredibly high.
Oh, incredibly.
It's an industrial control system layered over highly sensitive electronics. The absolute worst-case scenario isn't a pump failing, it's a leak. You have conductive fluid running inches away from high-voltage, mission-critical silicon.
And SCC's architecture actually anticipates this through CDU leak trigger events. This is where the platform moves beyond just telemetry and into automated policy enforcement.
Okay, how fast does it react?
Instantaneously. If the pressure sensors detect a drop that's anomalous with the current pump output, or if a physical leak node triggers an alert, the system does not wait for human intervention.
It executes a leak protection policy instantly.
Yes. The system will autonomously cut the auxiliary power to the affected units, or even toggle the AC circuits on or off the exact millisecond a leak is validated.
Wow.
It physically isolates the hardware to prevent a catastrophic short circuit from sparking a fire or, destroying millions of dollars in adjacent infrastructure. And it manages this alongside the traditional air-cooled servers in a single hybrid interface, which perfectly matches that brownfield reality we talked about earlier.
That is wild. But allowing a software platform to autonomously execute hard power cuts to production servers, that brings us right back to the governance and security perimeter.
It has to.
Because if a threat actor compromises the SEC control plane, they don't just steal data, they can physically power down the data center.
Which completely explains the intense focus on compliance and robust telemetry auditing in SEC. To secure that RBAC vulnerability we mentioned earlier, SEC leverages seamless Active Directory integration alongside strict SSL security compliance for all encrypted data transmission.
So by linking RBAC directly into the Enterprise Active Directory, you eliminate the threat of orphaned local accounts.
Exactly. The moment a network engineer's role changes, or say they exit the organization, their permissions to interact with the physical infrastructure are revoked globally. The metadata context is maintained centrally.
It also maintains a highly aggressive multi-tier alert agent, right? Administrators can set customizable policy conditions for specific alerting thresholds.
Yeah, so you can differentiate between, say, a localized fan failure, which might just log quietly to a dashboard, and a pressure drop in the CDU.
Right, a pressure drop needs immediate attention.
Exactly. A pressure drop triggers an HTTP relay and routes through Support Advisor to immediately page the on-call facilities engineer.
And what's fascinating here is how the platform utilizes the centralized logs repository and its advanced analytics engine.
Oh, the predictive side of it.
Yeah, it's constantly indexing this historical trend data for real-time visualization through charts and tables. But it isn't just generating backward-looking compliance reports. It actually applies predictive analytics to trace performance anomalies before they escalate into hardware failure.
Which is a huge paradigm shift. Instead of reacting to a server crashing from thermal overload, the analytics engine can detect micro trends.
Right.
It might notice that the liquid cooling pump resistance for Rack 4 has increased by, say, 2% over the last month, while the CPU temperatures are simultaneously creeping up by fractions of a degree, despite the workload remaining completely static.
So the system correlates those disparate data points across the physical and logical layers.
Yep, it flags the anomaly, alerting the administrator to a developing localized thermal issue, perhaps a degrading pump bearing or a microblockage in a cold plate, weeks before it triggers a critical thermal shutdown.
It forces a shift from reactive firefighting to proactive preventative infrastructure science. So, synthesizing everything we've pulled from the Supermicro team's analysis today, SuperCloud Composer is essentially built to absorb the inherent chaos of modern scale.
That's a great way to put it.
It takes a deeply fragmented, multi-vendor hardware reality, standardizes the communication through a Redfish API message bus, and orchestrates everything from dynamic NVMe storage pooling to physical liquid cooling valves. And it secures that immense power with Active Directory integrated RBAC, wrapping it all in a predictive analytics engine that sees failures before they even happen.
It fundamentally changes the role of the IT administrator.
Yeah.
You are no longer acting as a mechanic, manually tuning individual servers. You become an orchestrator, managing policies and defining outcomes while the platform handles the granular execution across the hybrid environment.
So what does this all mean for you? If you are architecting networks, managing enterprise tech stacks, or simply trying to understand the physical realities required to keep the cloud afloat, platforms like SEC represent the only viable path forward. The sheer volume of telemetry generated by modern AI and software-defined workloads has just bypassed human cognitive limits.
Oh, long ago.
We cannot sustain this scale of digital growth without infrastructure management that acts autonomously.
And that actually raises an important question, kind of a thought experiment to consider based on the trajectory of this technology.
Back in, listener.
We've established that SEC natively manages advanced AI infrastructure and GPU servers via standardized Redfish APIs. The platform exposes the physical levers of the data center to the software layer.
Right.
So as distributed AI workloads become exponentially more complex and capable of analyzing systemic efficiencies, how long will it be until the AI running inside those GPU clusters begins interacting directly with SCC's APIs?
Wait, you're talking about the workload analyzing its own thermal constraints and directly querying the message bus to request more physical cooling.
Exactly. How long until the AI autonomously monitors its own hardware degradation and just adjusts the liquid cooling flow rates, or shifts the dynamic power distribution based on its real-time computational pipeline, entirely bypassing the human administrator?
Oh, wow.
We are looking at the foundation for a completely self-regulating, self-optimizing data center where the software literally tunes the physical building it lives inside.
A closed-loop system, where the workload and the infrastructure become indistinguishable from one another. That is a profound concept to leave you with. Because managing a data center today might be like flying a jet with instruments scattered across different rooms, and SEC puts all those dials back into a single unified cockpit. But the underlying architecture suggests the ultimate destination isn't just a better cockpit. It's building an autopilot so deeply integrated into the plane's physical mechanics that eventually the pilot becomes obsolete. Thank you for joining us on this deep dive. Keep questioning the systems around you, and we'll see you next time.